Hey, Honors Physics. A few advanced students who have mastered how to handle the net force on charges in a straight line and the equilibrium problems have been asking about these triangle problems. We did not spend time on them directly in class, but they are a great application for students who might be going on and doing maybe AP Physics or college physics. So they really don't have any new skills, except for the fact that your three charges are laid out not in a straight line, but in a triangle. And I hope you can tell that this is actually a right triangle, where there's a 90-degree angle in this corner between Q1, Q2, and Q3. So it's a small little right triangle. Now, in this case, this is pretty challenging. It's not even the first one in the packet, but we're going to take a look at this. And we're only going to take this problem a little bit down the road, just to kind of have a glimpse as to what you do. So the question is, if you wanted to find the net force on Q1, that's up here in the upper left corner, you have to ask yourself kind of like the same questions that you would do in a straight line. You would ask yourselves, what does 1 do to 2? And then pretend Q2 isn't there. Just kind of imagine it being hidden. And what does Q3 do to Q2? Well, you know, we know that they're both there, but you have to figure out the individual forces that are acting on Q1. So let's refocus this and ask ourselves, okay, just like we did with forces in a straight line, we've got a positive 3 and we've got a negative 8. That's 1 and 2. And we know that those two are going to attract each other. Okay? So if someone said, draw the free body diagram on Q1, you would say that Q1 in the upper left-hand corner, the negative 8 microcoulombs, is experiencing one force that's straight down in the y-axis. That would be force 2 on 1. And we could find that force. We have Q1, we have Q2, we have the distance of separation as 0.06 meters, and we know the K value. So there's really no challenge to finding that after you have mastered Coulomb's law. But then you have to ask, okay, let's pretend Q2 isn't there. We can do that little trick that I did before where we kind of maybe mask it. Okay, and what would Q3 do to Q2? Well, we've got a negative 8 and we have a positive 7. So those would attract each other, right, mutually. So if I were to draw the free body diagram, I would draw it over here. And now these two forces are not in a straight line. They're on angles. But we spent a lot of time this fall examining how to add vectors that are not in a straight line. Let's clean up this box that I drew earlier. Let's see how we do that. We'll highlight this box. There we go. Delete it. Okay. So let's examine what's going on here. Okay. We've got a red force that's F21. So how would we set that up? That would be force 2 on 1 equals K Q2 times Q1 over the distance of separation. So we would have 9 times 10 to the 9th multiplied by, oops, I'm off the screen, 8 times 10 to the negative 6th and 3 times 10 to the negative 6th. So 8 times 10 to the negative 6th and 3 times 10 to the negative 6th. I may have changed their order. And the distance between them is 0.06 meters. That's what it says. And we are prepared to calculate that. But then when you calculate it and you get a final answer, you're going to ask yourself, that's in the y-axis. It's in the negative y direction. So according to the free body diagram, that would be a y force, right? It doesn't need an x component. It would be straight down. But the blue force, on the other hand, is a little bit more tricky. So the blue force is at a 45-degree angle relative to the horizon. And we know that because the triangle has a 0.06 and a 0.06 for the two legs. So if you have the same side there, you know that this must be 45 degrees So this must be 45 degrees. Okay? And the only thing that I think is going to make that a little challenging is if we set up force 3, 2, we would still have to do K, Q1, Q3 over distance squared. 9 times 10 to the 9th. Q is 8 times 10 to the negative 6th. The 3 is 7 times 10 to the negative 6th. But how far apart are they? Well, in a right triangle, you can find the hypotenuse, especially if it's called a 45, 45, 90 triangle, by remembering that the sides, this is a shortcut, not something that everyone necessarily remembers, but if the two sides are the same, they're x, then the hypotenuse is going to be x times the square root of 2. So your distance is going to be 0.06 times the square root of 2, which is about 1.4. And your calculator will take care of that for you. So that is the beginning of how you'd set up a triangle problem. The details on how you actually add the forces is an older skill, and anyone who really wants to pursue that certainly can seek me out. This is kind of enrichment going above and beyond what's expected for Wednesday's test on electrostatic calculations.